page 51, the first wee section is on car safety, questions 1 and 2. And there's question 1, is a person not wearing a seatbelt thrown forward? No. A person not wearing a seatbelt is not thrown forward. And we'll explain why in part B. So basically what we've got to discuss is the motion of the car and the motion of the passenger and use Newton's laws. So if the car stops suddenly, that must be an unbalanced force, doesn't it? So an unbalanced force is acting on the car causing it to decelerate. So there must be an opposing force by Newton's second law. But the passenger is not attached to the car. So the passenger has little or no force. They might have a wee bit of friction basically between them and the seat, but it's going to be pretty negligible. Acting on them, so by Newton's first law, they continue at the same speed, in the same direction as they were previously. So for instance, if they were in a car going at 30 miles an hour, then they were going at 30 miles an hour. So that's why it might appear that they're thrown forward, but they're just continuing forward at the same speed while the car slows round about them. And obviously, eventually then they might go on and hit the windscreen or the dashboard, steering wheel, something that injures them. And we'll look in question 2 about the difference between hitting something hard and hitting something soft. If you are wearing a seatbelt, then we've got the same idea. There's an unbalanced force acting on the car, causing it to decelerate. The seatbelt provides an unbalanced force on the passenger. Say they're attached to the car, that's an opposing force that's stopping the car. So it'll be an opposing force on them, bringing them safely to a halt by Newton's second law. And like I say, in the next question we'll look at the difference between being stopped by a seatbelt, which has got a wee bit of give, and something hard like the steering wheel or a dashboard. So both of them apply an unbalanced force to bring you to a stop. So number 2, let's start with some calculations. So calculate the decelerating force on the driver with no airbag. So first of all, we're going to have to work out the deceleration and then work out the force once we've got that. So listing our variables, what we know. And basically the only difference between the two is the time which you decelerate in. But we'll see what difference that makes. So first of all, A equals V minus U over T. And because the time involved is very small, we end up with quite a large value for deceleration, minus 413.79. Remember, don't worry about significant figures in the middle of a calculation. we'll deal with him at the end. And then we can work out the unbalanced force is 65 multiplied by that acceleration. And so we get an unbalanced force of minus, and this time we will round off to two significant figures because all the data in the question is given to 2. You could go to 3 as well. But we get minus 27,000 newtons. If we do a similar calculation now, so we've got the same value for u, because whether or not you're wearing a seatbelt doesn't affect the speed the car's going at. If you come to a rest, your value for v is going to be the same. But what we can do is control the time for that stop to take place. We can't change the mass of a driver. So exact same working. But with a bigger time involved, we should get a smaller acceleration. Oops. So we get minus 31.58 this time, and then when we do our F equals ma calculation, we get minus to two significant figures. The unbalanced force is minus 170 newtons. So significantly smaller, protecting the passenger. So part C, an airbag increases the time for deceleration to take place. Now try and avoid phrases like it slows down the deceleration, because slowing down and speeding up are words that we use to describe speeds or velocities, not accelerations or decelerations. So increases time for deceleration to take place. This decreases the value of deceleration. And so decreases the force on the driver. Okay, question 3 goes on to deal with free fall. So using equations and a free body diagram, explain why in theory all bodies, irrespective of mass, should accelerate downwards. So in actual fact, it's a very simple free body diagram. For something in free fall, right, then the definition of free fall is that the only force acting on the object is its weight, W. So we can say that the unbalanced force is equal to the weight, because that's the only force there. But we have formulas for unbalanced force and we have formulas for weight. So unbalanced force can be written as ma. Weight can be written as mg. And what we can do now is divide both sides by m. Because it appears on both sides, we can simply divide both sides by that, and we're left with A equals G. So if there's no other forces acting, only weight, then the m cancels out on both sides, and you're left with the acceleration is equal to the acceleration due to gravity. And that's because we're ignoring other forces like air resistance, okay, which would be the most common one, which would affect this in reality. If we go back to A again briefly, just basically an object with a larger mass will have a larger weight pulling it down, but because it's got a larger mass, it needs a larger force to get that same value of acceleration. That's why it cancels out on both sides. If we go into part C, when this force is taken into account, what effect does it have it downwards? So an object with a large surface area, So think, for instance, parachute. I'll change that word slightly actually. Will experience a lot of air resistance. Which decreases the unbalanced force. Okay, because it's opposing the motion. In this case, the object's moving down the way, the air resistance is acting up the way. Decreases the unbalanced force and decreases the acceleration. And then simply D, textbook value for G we can write as 9.8 newtons per kilogram, or as we've seen, that's equivalent to an acceleration, so you can also write it as meters per second squared. And we're not going to go into the detail of proving that, but we saw in part A that A is equal to G, so acceleration and gravitational field strength are equivalent units for that as well. And now on to question 4 about terminal velocity. So frictional force felt by a body moving through a fluid. It can be called drag or fluid resistance. So for instance, we were talking there about air resistance if the fluid is air. You can talk about air resistance if you're moving through water. You could talk about water resistance. And B, and remember, a body in physics just means an object. So as a body's velocity increases, frictional forces also increase. Now we're not going into the detail of that relationship. It's not a simple linear relationship, but just need to know the idea that as one increases, the other increases. So for example, if we look at a parachutist immediately after she's jumped out of an aeroplane, okay, at that point, just immediately as she jumped out of the aeroplane, she's not had a chance to build up any speed, so there's no air resistance. So at that point, the unbalanced force is equal to W. And so our motion at this point is she's an unbalanced force pulling her downwards, so she will accelerate. Just at that first instant. But, as we were just discussing in part A and B, as she starts to accelerate, she starts to get faster, then frictional forces, drag, air resistance are going to increase. Okay, so when we go into part E, we've got an idea of her reaching a terminal velocity. And terminal velocity is the idea of balance forces. So our weight hasn't changed, but what has happened is that the drag forces opposing her have increased until at that point they're balance forces. So forces are balanced, or another way of saying that, there's no unbalanced force. Now, by Newton's first law, you can say if forces are balanced, then our velocity must be constant. Or you could say by Newton's second law, the acceleration is zero, so the velocity is constant. So you can justify it using Newton's first or second law. And that constant velocity is called our terminal velocity. Now, if she opens her parachute, we're going to have a similar sort of free body diagram. Our weight hasn't changed throughout all of this, but now all of a sudden by opening the parachute, we have dramatically increased the drag. Okay, it'd probably be, in this sketch here it's roughly double, but in reality it'd probably be a lot bigger. So at that point we've got a much bigger value of drag. So during the next few stages of motion, so now we have an unbalanced opposing force, an unbalanced upwards force, while she's moving downwards. So the unbalanced force is upwards, while she is moving downwards at whatever her terminal velocity was. So you have this opposing force which is going to cause her to slow down. She's not going to instantly start moving up the way just because you apply an unbalanced force. You'd have to slow down first of all. So when you open a parachute, you don't go shooting up quite often because the camera is also falling, and when you open the parachute you slow down dramatically. It looks like you move up when you see pictures of it, but you're not actually. So she's going to decelerate over the next few minutes. But as she does so, because she's slowing down, the drag forces decrease. Until once again they balance the weight. And a new slower terminal velocity is reached. So the forces are the exact same as they were the terminal velocity without the parachute open, but the speed to get that same force is much slower because of the bigger surface area. So that leads us nicely into part H. Once again, we're back to weight and drag being equal sizes of forces, opposite direction. And then lastly, for this question, a sketch the entire motion. So it's a shape really that's important for this. So I've got a graph of velocity versus time. Always good to mark your origin, so you can be quite fussy about that. And really we've got kind of 4 distinct parts to the motion here. We've got the idea that at first when she jumps out the aeroplane, she's accelerating, but it's not a constant acceleration. Most of the motion we've done up to this point has been constant acceleration. But here you've got a changing force. But what we end up with, remember, is a terminal velocity. So we end up with a flat bit in the middle. That's not very well drawn. I'll try that again. Use a roller this time. Roller slipped a wee bit on the screen, but you get the idea. So there's our first terminal velocity, right, with our parachute closed. So that's a kind of first section. There, accelerating. Section 2 is her terminal velocity. Then when she opens the parachute, once again we get a curved section. We have a rapid deceleration with this open parachute. That's section 3. And then the last bit we have the new lower terminal velocity. So we want a straight line again for that. That's a new lower terminal velocity. So it's these shapes. Curve for section 1, flat for section 2, curve for section 3, flat for section 4. And the last one, number 5. Why does a car have a top speed? So When the car applies its maximum engine force, it will start to accelerate. As it does so, drag forces, and here we are kind of combining in the one, both the air resistance of pushing through the air and frictional forces as it rubs against the ground. So as it does so, drag forces will increase until they balance the engine force. And balance forces means constant velocity. Now all this assumes a flat road. We're not looking at it, car moving up or down hills. So at this point, the car will have a constant velocity. Due to Newton's first law. And that constant velocity is what we call its top speed. Okay, it can't go any faster than that. And then B, so basically if you want the car to go faster, there are two things you can do. Right. To have a larger top speed, you can increase the engine force. Okay, a more powerful engine, or decrease the drag forces, e.g. by making the car more streamlined. So the main differences between a sports car and a farm car, for instance, would be lower down to the ground, smoother shape, all these streamlining ideas, and an engine which can produce a larger force.